Let's jump right in. Welcome to This Explainer. Today, we're diving into what is honestly one of the most underappreciated, beautiful formulas in all of mathematics. The most beautiful formula not enough people understand. We're going to build a bridge from basic geometry to a seriously mind-bending twist about higher dimensions. And more importantly, we'll see exactly how we can map them. But to reveal this beautiful unified theory, we kind of have to start somewhere familiar. We have to start with a puzzle that looks purely numerical at first glance. So here's the question. If you choose two random numbers, x and y, both between -1 and +1, what is the exact probability that their squares add up to 1 or less? Now sure, that sounds like a dry, analytical puzzle. You could easily pull out a notepad and set up some nasty integrals to figure it out. But this question is actually screaming to be answered visually. Think about it. Imagine drawing a square that goes from -1 to +1 on both a vertical and horizontal axis. That gives you a 2 by 2 square, right? Now that condition, x squared plus y squared being less than or equal to 1, that mathematically describes every single point inside a circle with a radius of 1. So visually speaking, you're really just picking a random point inside that 2 by 2 square and asking what the exact odds are that it lands inside the circle drawn within it. The answer? It's simply the area of the circle divided by the area of the square. It's an incredibly elegant visual solution to an algebraic problem. Which brings us to section 1, the reality of high dimensions. We are going to stretch our minds way beyond our comfortable 3D world to see what actually happens when we push into higher dimensions. Now, you might be asking yourself, why do we even care about dimensions beyond the 3 we live in? It sounds like pure math fiction, right? Well, far from being some useless theory, 100-dimensional geometry is entirely real, and it serves as the literal engine under the hood of today's AI. Representing data in machine learning relies entirely on high-dimensional spaces. When you interact with large language models like ChatGPT or Claude, they aren't thinking in words. They are converting chunks of text, concepts, and ideas into incredibly long lists of numbers. And each one of those lists can be plotted as a single coordinate point in a massive, high-dimensional space. So navigating these high dimensions isn't just a fun thought experiment, it is absolutely crucial. It's the fundamental basis of modern technology. That leads us perfectly into section 2, when our intuition fails. Here's the crucial point. If we blindly trust our basic 3D instincts when traveling to these higher dimensions, the geometry is going to severely punish us. Let's look at this classic mathematical fable. It's called the bounding box puzzle. We want to know, as dimensions increase, how big does a central inner sphere get? Okay, imagine a 2D piece of paper. Draw a square bounding box. Now put a unit circle at every single corner so they perfectly fit inside. Then place a tiny new circle in the dead center and grow it until it just perfectly touches those outer corner circles. Got the visual? Awesome. Now scale that exact same mental exercise up to 3D. You have a cube bounding box, a sphere packed into every corner, and you grow a central sphere from the middle. As we step up the dimensions, adding more and more coordinates to this box, what actually happens to that central sphere? Well, the math reveals a completely fascinating pattern. In 2D, the inner circle's radius grows to about 0.4. In 3D, our central sphere's radius hits 0.7. So far, so good, right? Everything feels completely normal and intuitive. The inner sphere is just taking up a bit more room as we add dimensions. But watch what happens by the 10th dimension. Applying the exact same scaled-up Pythagorean theorem, the inner sphere's radius has suddenly ballooned to over 2.16. Just take a second to let that sink in, because this brilliantly illustrates a totally mind-bending paradox we're about to uncover. Think about the physical implications of a radius of 2.16. In our 3D bounding box, the central inner sphere safely fits completely inside the outer walls. But since the distance from the center origin to the box's flat edge always remains exactly 1, regardless of the dimension, an inner sphere in 10 dimensions with a radius of 2.16 literally pokes completely out of the box. I mean, how can a sphere completely contained by corner spheres break through the walls of its own box? It completely busts outside the boundaries that supposedly contain it. It just pierces right through the sides of the high-dimensional cube. Now, it's pretty common to hear people say this happens because high-dimensional spheres must be quote-unquote spiky, but that is entirely wrong. Spheres are perfectly round by definition. They're exactly an equal distance from the center at all points, no matter how many dimensions you add. It's actually the cubes that are the problem here. The bizarre reality is that the corners of a high-dimensional cube stretch infinitely far away from the center. To get to a corner in 10 dimensions, you have to travel a long distance across 10 different perpendicular axes. So the corners are stretched way, way out. Because our corner spheres are shoved deep into those distant corners, the central sphere has to grow massive just to reach them. That is what makes high-dimensional cubes terrifyingly spiky and entirely counterintuitive. Section 3. The Archimedean Knight's Move. To stop getting tricked by these spiky cubes, we need a reliable pattern to map higher dimensions. So let's start with what we actually know. Notice how the boundaries here are essentially just the calculus derivatives of the interiors. Let's trace it out step by step. Look at 2D. The equation for the interior area is pi r squared. If you take the derivative of that, you get 2 pi r, which perfectly describes the boundary, the circle. In 3D, the volume is 4/3 pi r cubed, and its derivative is 4 pi r squared, the surface area. Taking a derivative mathematically represents finding a boundary, and going the other way, taking an integral of the boundary effectively finds the interior volume. It's like a mathematical puzzle fitting perfectly together. But how do we actually jump the fence from 2D up to 3D? Well, the ancient Greek mathematician Archimedes proved a brilliant area-preserving trick. He showed that if you project a sphere's surface area outward onto a cylinder that perfectly encloses it, something magical happens. As you map the curved sphere outward onto the flat cylinder walls, the geometry stretches horizontally around the equator. But because it's casting a shadow from the center out at an angle, the top and bottom regions near the poles get perfectly squished vertically. The horizontal stretch and the vertical squish perfectly cancel each other out, meaning the total surface area is entirely preserved in the projection. And here's the best part. We can use this Archimedean trick to reliably step up through the dimensions without our intuition failing us. By combining basic calculus with Archimedes' trick, we can hop up and over a mathematical grid like a knight in chess to calculate the volume of any dimension. It's a two-step process. Step 1. You step right. You multiply your previous interior by 2 pi to project the boundary into a new dimension. Step 2. You step down. You use calculus to integrate that boundary, which effectively means you divide it by the new dimension number, n, and that gives you the brand new volume. Remember that step. You absolutely must divide by the dimension number n. Step right, step down. Multiply by 2 pi, divide by n. Section 4. The beautiful unified formula. Let's move on and see exactly how this knight's move pattern builds one of the most underappreciated formulas in all of mathematics. If we just repeatedly apply this knight's move, multiplying by pi and dividing by the dimension number over and over, we end up with this incredible formula for the volume of a sphere in any dimension. By constantly dividing by the dimension number, we create a beautiful equation governed by factorial in the denominator and the number pi in the numerator. It even seamlessly handles odd-numbered dimensions, requiring half integers for odd dimensions where 1/2 factorial equals the square root of pi over 2. This ties into what's known as the gamma function, which is basically just a clever mathematical tool that lets you calculate factorials for fractions. It makes the whole formula perfectly smooth, whether you're in the second dimension or the 99th. Section 5. The Vanishing Sphere Twist. We have our beautiful unified formula, but what actually happens when we push this elegant formula into truly massive dimensions? Tracking the volumes of a unit sphere across dimensions reveals something truly unexpected. The volumes rise naturally at first. 3D is 4.19. 4D goes up to 4.93. They peak at the 5th dimension at 5.26. But then they hit a brick wall. Shockingly, the volumes begin to shrink. By the 7th dimension, the volume drops to 4.72. The spheres are somehow losing space inside them. Check this out. If we run our formula for a 100-dimensional unit ball, the volume plummets to an infinitesimally small, downright puny decimal, 2.37 times 10 to the negative 40th power. That is 0.000, and you just keep going for 40 zeros until you finally hit 237. It essentially becomes nothing. A 100-dimensional sphere contains practically zero volume. So why on earth does this happen? The culprit is our knight's move formula. Think about the math here. Every single step, we multiply by 2 pi, and we divide by the dimension number n. When n is less than 2 pi, which is roughly 6.28, the multiplication wins out. So for small dimensions like 3 or 4, the volume grows. But once the dimension number n grows larger than 2 pi, the division entirely swallows the math. The larger n gets, the harder that continuous division crushes the volume all the way down to zero. And what's even crazier is where that tiny remaining microscopic volume actually lives. Incredibly, in 10,000 dimensions, practically 100% of a sphere's volume is flattened right against its boundary equator. The volume doesn't just vanish evenly, no. It gets pushed entirely to the outer boundary skin, meaning the interior of the sphere is effectively empty space. If you peel away just 1% of the outer layer of a 10,000 dimensional sphere, you remove over 99.99% of its total volume. That is wild. Beauty in math requires looking at the familiar in the context of the general. So, does the spiky reality of high-dimensional cubes and the vanishing empty interiors of high-dimensional spheres break the universe? Not at all. It simply proves that true mathematical beauty is only visible when we step back and look at the generalized whole. To find the beautiful formula governing all geometry, we had to stop trusting our narrow 3D intuition and instead trust the math, trust the patterns. If our intuition fails so spectacularly at just 10 dimensions, what other hidden truths are waiting to be uncovered in the thousands of dimensions where our modern AI currently lives and breathes?